Okay, so I decided to add on this extra little short video, hopefully it'll be short, to really get into the precise definition of a limit. This is something that we really should have done in Calc AB. My problem is that it feels like such an overwhelming topic, especially because it happens in week 1 of school, that I've just done what AP did, which is completely ignore it. They never even bring up the precise definition of limit. But to be a full calculus class, I feel like I at least need to show you and maybe let you try a couple problems yourself if you want to. But the precise definition says that the limit as x approaches a of f of x equals L if for every number epsilon greater than 0, there exists a delta greater than 0, such that if this part, 0 is less than absolute value of x minus a is less than delta, then absolute value of f of x minus L is less than epsilon. I've seen it, I've seen it listed this if, that is true. And the weird part about it is that we say, we start with the if part and kind of prove the then part. But when we prove it, we actually kind of start with this part. And I'll show you proof in a second. But let's start with finding some deltas given specific epsilons. If we're finding this limit in general, we would plug and chug. 1 minus 1 is 0. Over 0, we would apply L'Hopital's. The derivative of e to the x is e to the x minus 0. Derivative of x is 1. E to the 0 is 1 over 1. So we found it using L'Hopital's. However, we need to find some values of delta given an epsilon. And by the way, if I go back to this precise definition, if we have my favorite graph, some A right here, the graphical look, here is our L clearly because the function goes right there. This says for every epsilon, which by the way, if I solve for f of x, remember, a less than turns into a sandwich problem, right? And so add L to both sides. We'd have L plus epsilon is less than f of x is less than L. That was a negative. L minus epsilon is less than f of x, which is less than L plus epsilon. Yeah, when we sandwich between positive epsilon and negative epsilon. So this epsilon is some little area around the limit, right? And what happens graphically is we can find, just run that point down here, run that point down here, and we can find a delta. Now, interestingly enough, on my little graph, if you can see it, it certainly looks to me like the delta on the right side of the A is smaller than the delta on the left side. So what happens is sometimes that's the case. And so I could not choose my delta to be this bigger part because if I ran that same distance over here, I'm out of the L minus epsilon spot, right? So all you have to do is choose the smaller delta on whichever side of that A value. That's the idea of finding those deltas. So that's what we're going to do here. We're going to set up that, remember, it's f of x minus the L, in this case it's 1, less than epsilon, right? And the x minus 0 is less than delta, right? So we just are going to take our f of x minus 1, and we're going to crank it out on the calculator. That's the only way I can think of doing it. So let's put it into y equals that f of x minus 1. So fraction bar, e to the x minus 1 over x minus 1. And so that's my function right here. And we want the absolute value to be less than epsilon. In other words, we're going to say this less than 0.5 and greater than negative 0.5, correct? That's the little idea. So I'm just going to go here and put positive 0.5 here and negative 0.5 there. And I just want to see where the things cross. Oh no. Maybe I need to take that one off. All right. So I want to see where the things cross. I cannot get any picture there, so I'm just going to say window, -5 to +5. We're going to, let's just go like -2 to +2. See if that will give us a picture of what's going on. Oh, we see that top, we see both intersections, right? So find the second trace intersect those two curves. All right, so it looks like the 1 delta, because we're going just to the right and left of 0, right? So the 1 delta is approximately 0.76, let's just say round up to 3. It's really smaller than that, so let's just keep it down to 2. Because remember, it's less than delta, so we can pick anything smaller than that, right? And then second trace intersect. I'm going to go that curve near there. Uh-oh, not that one. That other one. The y equals -0.5, right? Oh, that delta is -1.59. Well, we'll just keep it down to 3. So, bottom line is, we can't pick the delta. Oh, by the way, that was, x is sandwiched between positive delta and negative delta, right? So, we can have a negative number, but it's an absolute value kind of thing. So we can't pick 1.5 because on the right side, 1.5 would have been out here outside of my little area. So bottom line is choose the smaller one. So for this one, delta is going to be, probably less than 0.762. Any number, you could just call it equal to. And honestly, I would have to accept any number for my delta less than that because it would guarantee this part is true, right? So this is also like a part of calculus that is a little bothersome because, anything less than that whole number, 0.7626, whatever. So we could have had 0.7621 or whatever. And the only thing we need to do differently if we're finding with the epsilon 0.1 and negative 0.1, we're just going to see those deltas are smaller and smaller, right? I think I'm going to get my window a little closer. -1 to +1. Hopefully we'll be able to see a little bit better. All right, second trace intersect. So this one, the delta is approximately 0.1877. And by the way, we kind of knew what happened on the other one, so I'm going to probably just choose 0.187 or something like that. But let's go ahead and find that other intersect. Got to change to that other one. -0.215. So I'm going to choose the smaller here. Delta is going to be anything less than 0.187. So, not a beautiful thing, but I did want to expose you to it, and I will give you a couple problems you can test yourself to see if you can do it. Now, if we're proving this limit, then what happens, if you remember, I always had the thought cloud thing. I will say, usually, I want it to actually be a part of my proof in this case, because we're doing that same idea of, the f of x minus the limit, got to be less than epsilon, right? And then we're going to say absolute value of x minus 3 less than delta, right? So what we have to do is we have to manufacture what delta we're going to use. And so that f of x is 4x minus 5. And then I just start working on this to actually make it look like that, okay? -5 minus 7 is -12. Factor the 4 out. And some magic always ends up happening here, especially on the linear ones. If you try to do a quadratic one, it becomes a little bit tricky, because what you have to do is say, well, randomly, if you factor out a 4 plus x or something, or an x plus 4, you have to kind of substitute some number for that. And that's, again, it becomes not the super preciseness that we want. So look at the magic that occurred. We now know what our delta needs to be, right? So if absolute value of x minus 3 is less than delta, which is equal to epsilon over 4, then work through all these steps backwards. But since all the steps are shown, shown above, uh, 4x minus 5 minus 7, absolute value is less than epsilon. Our proof is done. Sorry. I don't know if that helps or not. But anyway, hopefully that will be enough to at least expose you to this idea of the precise definition of limit. Some problems, if you want to just to practice yourself, there's 41, 43, something like that, through certainly 45 odd, so you can look in the back. A bunch of them have these absolute value things. I'm not sure if I would do those. I would do 46 is a good one. 48 would be a good one. Maybe even 49. 49 is just a constant. So that's going to be kind of a weird proof. But anyway, those would be a couple you could look at. Finding some deltas and then a couple of just linear proofs. Good luck and have a good day.